Hello and welcome to this three-part presentation on a global deflection equation for prismatic beams. The first part of 8 slides takes us as far as a derivation of the global deflection equation for multipoint partial linear loads. The second part, again of 8 slides, shows us how to use the same equation for solid partial linear loads. The final part of 10 slides looks at nonlinear loads, global slope, moment and shear equations. It also includes various properties and symmetries amongst the deflection equations and beams that this formulation highlights. To start off with, I thought I'd say a few words as background to the work presented here. But if you want to skip this, then move ahead to about 2 minutes 45 seconds. I did most of this work back in 1985 as a physicist working on a theoretical project on the response of various beam-like structures to impact loading. I'd never heard of beam theory before, so I looked it up in an engineering textbook and was horrified at the number and complexity of the beam equations. I had hoped that there would be just one deflection equation that I could plug into my own equations, but the 4 different beam types and 3 linear load profiles covered in the book required 12 different deflection equations to describe. And for partial loads, this became 36 equations, as a separate deflection equation was required for the 3 regions either side of and underneath the load. I tried to find a relationship amongst these equations but couldn't, so I decided to try to derive a single all-encompassing deflection equation myself, and this is the result. I call my equation global as it applies across the whole beam with a partial load, unlike the 3 regional deflection equations normally required. The one relationship I could find was between the 2 deflection equations either side of a single point load on each beam, so that was my starting point. As such, my method can't be said to be from first principles, and I don't claim that it is. It's just a way of deriving a single deflection equation that works across the entire beam for many beam partial load combinations, including both linear and nonlinear loads. And by repeated differentiation of the global deflection equation, it's possible to derive a single global slope, moment and shear equation for all these combinations. If you want to follow the method in more detail, there are comprehensive notes on my website at www.gammamunew.co.uk with additional worked examples. Before we get started, I'll give a quick overview of the applicability of the global deflection equation. It applies at least to 4 beam types: a cantilever beam, a fixed end beam, a propped cantilever beam, and a simply supported beam. It may apply to other beam types as well, or to composite beams, but these 4 are the only ones I considered. I based the initial linear load shapes on a multipoint load because the only symmetry I could find was for a point load. The default shape I chose was a falling trapezium-shaped load with equally spaced point loads. I chose this shape because I could generate a rising trapezium-shaped load, a rising triangular load, a falling triangular load, and a uniform load just by adjusting the magnitudes of the end point loads. Once I had a global deflection equation for this multipoint load, I then transformed it into a solid load by letting the distance between each point load go to 0, whilst keeping the load width constant. This gave me the same 5 load profiles, but this time for solid loads, which is what I wanted. Once I had the load profiles sorted, I then looked at the 3 regions to the left, underneath, and to the right of the partial load. All this resulted in 60 beam load regional deflection equations, which I managed to squeeze into a single global deflection equation, described by the matrix equation 6EI y of x is equal to UAX plus j over L to the power p times v dtx. The derivation and use of this deflection equation is the subject of this presentation. As well as describing linear loads, this equation can also handle nonlinear loads, either specific ones like parabolic or sinusoidal loads, or general power series loads. In addition, by repeated differentiation, we can derive global slope, moment and shear equations, as well as a general load equation. We'll also see how this formulation of the global deflection equation gives rise to a number of symmetries or equivalences amongst the beams and equations, which may or may not be already known. To start with, we'll look at the single point load deflection equations for the four beams we're interested in: a cantilever beam, a simply supported beam, a propped cantilever beam, and a fixed end beam. Each beam is of length L and has a single point load of magnitude F, situated a distance A from the origin, which is at the left-hand edge of the beam. The coordinate system is such that y is positive upwards and x positive to the right. The naming convention used is that the deflection equation to the left of a point load will be called yL of x, and to the right of the load yr of x. YL of x and yr of x are shown here for a cantilever beam. What's immediately apparent is that these equations are symmetric with respect to a and x, and that the same is true for the other three beams. This symmetry will play an important part when we look at the matrix formulation of YL of x and YR of x later. In the previous slide, we saw the deflection equations YR of x and YL of x written out as normal equations, but they can also be written in matrix form as follows. For example, for a cantilever beam, YR of x is equal to minus FA squared times 3x minus a all over 6EI. If we take out f over 6EI and introduce a 1/4 row vector with components of increasing powers of a 4×1 column vector of increasing powers of x, and a 4×4 matrix between the two vectors, then we can see by inspection what the elements of the 4×4 matrix should be. As there aren't any terms involving a to the power 0 or a to the power 1 in YR of x, the top two rows of the 4×4 matrix are 0. A squared is multiplied by a minus 3x, so we need a minus 3 in the third row, second column. And we need a plus 1 for the a cubed, which we get by putting a 1 in the last row, first column. All the other elements are 0. We can determine the 4×4 matrix for YL of x in a similar manner. I call these 4×4 matrices bending matrices because they essentially tell the beam how to bend. They are beam dependent, differing from one beam to another. If we call the bending matrix associated with YR of x D, then the bending matrix associated with YL of x is DT, the transpose of D. This relationship between the bending matrices is due to the AX symmetry in the original equations for YR of x and YL of x. If we introduce a constant k defined to be equal to j over 6EIL to the power p, where j and p are beam-dependent integers, and call the row vector A and the column vector x, then we can write YR of x and YL of x in the form YR of x is equal to KFA dx and YL of x is equal to KFA dtx. Note that bending matrix D is always associated with YR of x and dt with YL of x. In the last slide, I introduced the concept of a bending matrix and showed how both YR of x and YL of x could be written in matrix form. I've reproduced these matrix equations here along with the definition of K, which is a constant for a given beam. In the following table, I show the bending matrices for each beam, along with the values of J and P for each beam and the resulting expression for K. Looking at these values, it's immediately apparent that the cantilever beam stands out from the others in that the length of the beam L doesn't appear anywhere in K or in the bending matrices. And if we look at the difference d minus dt for the cantilever beam, all the non-zero terms lie on the rising diagonal, which isn't surprising as the only non-zero terms in d and dt lie on this diagonal. But the same is also true for the simply supported beam. Although it has non-zero terms off the rising diagonal in D, when we take the transpose, the same values appear in the same place, so cancel each other out when we subtract dt from d. The same behaviour is seen in the propped cantilever beam and the fixed end beam. We can also see that the elements in the rising diagonal of d minus dt for the simply supported beam are all L times the values of the corresponding elements in d minus dt for the cantilever beam. Similarly, all the elements on the rising diagonal for the propped cantilever beam are 2L cubed times those for the cantilever beam, and for the fixed end beam they are L cubed times the corresponding elements in the cantilever beam. This allows us to write a relationship between d minus dt for the four beams. If we call d minus dt for the cantilever beam matrix A, which is a constant matrix and so beam independent, then we can write the relationship as d minus dt is equal to L to the power p over j times A. This relationship gives rise to a surprising property of beams with a single point load, as we will see later. Okay, we've done all that we need to do with the beams. Now we need to look at the load. Here I'm going to use a falling trapezium-shaped load as the basic load profile. By adjusting the magnitudes of the end loads, I can make this into a rising trapezium-shaped load, a rising or falling triangular load, or a uniform load. So consider a generic beam having a multi-point trapezium-shaped load as below. There are a total of S individual point loads, each separated from its neighbour by a small distance b. The width of the load is d, which is related to S by the simple equation d equals S minus 1b, from which we get S is equal to d over b plus 1. This is an important equation which we'll use later when we come to convert a multipoint load into a solid load. If we focus on one of the point loads and call it Fm, where m is an index running from 1 to S, then Fm is situated a distance am from the origin, and we have the simple relationship that am is equal to a plus m minus 1b. From this we see that when m is equal to 1, we get that a1 is equal to a, another result which will be important later. The distance to the last load, as, is equal to a plus d. We can find an expression for Fm by considering two equivalent right-angled triangles. The blue triangle has a height f1 minus fs and a width d, giving a slope of f1 minus fs over d. The yellow triangle has a height fm minus fs and a width as minus am, giving it a slope of fm minus fs over as minus am. As these two right-angled triangles are equivalent, the slopes are the same, giving this equation. After a bit of algebra, we can isolate Fm, which can be written in the compact form Fm equals alpha minus beta am, where beta is defined to be delta f over d, with delta f equal to f1 minus fs. This makes beta the slope of the load. Alpha can be written in two ways, either as alpha equals f1 plus beta a, or alpha equals fs plus beta into a plus d. You can choose which one is the best for a given situation. For example, a rising triangular load would have f1 equal to 0, so the best equation to choose would be alpha equals f1 plus beta a, as this simplifies to just beta a, when f1 is equal to 0. The second form would be better for a falling triangular load, as fs equals 0 there. For a uniform load, the slope is 0, and so is beta. In this case, alpha can be written as either f1 or fs, or, as all the f's are the same, just let alpha be equal to a general load f. Note that a nonlinear load doesn't have a constant slope, so we can't use alpha and beta for nonlinear loads. These are used for linear loads only, and we'll see later how to handle nonlinear loads. If beta is the slope of the load, alpha is the projection of the slope onto an f-axis. For a uniform load, as we just saw, beta is equal to 0, and alpha is equal to the magnitude of any of the loads, which we can call general f, which will be positive. So when beta equals 0, alpha is positive. When beta is positive, which is falling to the right, alpha is also positive. When beta is negative, falling to the left, alpha can be negative, positive or zero, depending on the magnitude of the end loads and the position of the load on the beam. If the load is in the shape of a rising triangle situated at the origin, alpha will always be zero. We're now in a position to derive the global deflection equation. The derivation is very simple and takes only a few lines to complete. Firstly, consider a generic beam with a falling trapezium-shaped load as before. Choose the point X lying between the rth and the r+1th point loads, and let AR be the distance of the rth point load from the origin, and AR+1 be the distance of the r+1th load from the origin. Then we can write the general inequality that AR is less than or equal to X, which is less than or equal to AR+1. This inequality will be used throughout the presentation. The principle of superposition lets us write the deflection at point X as the sum of deflections YR of X caused by point loads to the left of X plus the sum of deflections YL of X caused by point loads to the right of X. The sum from R+1 to S can be written as the sum from 1 to S minus the sum from 1 to R, which gives us two terms with sums from 1 to R, which we can combine, leaving a single 1 to S summation. Then, using the matrix formulations of YR of X and YL of X, reproduced in the orange box, we get the sum from 1 to R of K Fm vector Am d minus dt vector X, plus the sum from 1 to S of K Fm vector Am dtx. And using the relationship for d minus dt derived earlier, the first term becomes the sum from 1 to R of K Lp over J Fm vector Am Ax, where vector Am is the multi-point load version of the single point load vector A. Looking at these two terms, we see that all the M dependence lies in the product Fm times vector Am. So if we define two new vectors u and v, such that u is defined to be the sum from 1 to R of Fm vector Am, and v defined to be the sum from 1 to S of Fm vector Am, then we can write the deflection at point X in the form 6ei y of x is equal to u ax plus j over lp v dtx. This is the global deflection equation.